We are used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things. Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards?
I'll try.
If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction, and we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is, the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind. What's happening this time? Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless, So what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference. I think if you concentrate on watching just the puck, you can see that it is moving in a straight line, and that therefore there is no unbalanced force acting on it. Now we're going to stop this rotation so that I can talk to you about what is happening here. I don't know about you, but I'm dizzy.